G'day everyone, my name's Paul Gammon, and on behalf of myself and James, and we're just going to talk today about some permafrost solute concentrations in an active gravel pit. Half-time results, because these are the first results we've got for this activity, which is part of the Environmental Geoscience Program's Permafrost project. Next slide. Not really going to go in the abstract in detail, just to say that this is looking at an active gravel pit that was used to build the Inuvik to Tuktoyaktuk Highway, or the ITH as it's more commonly known, and really we're trying to get at what is going on in water-rock interactions, permafrost thawing, freeze-thaw relationships, relationships between ice and water, and the geochemistry thereof. These are the prime project members at the moment. There are of course others involved, but these are the principal project members. The biggest problem I faced when I first started thinking about this, and then James and I started trying to solve it, really was along the lines of how do you solve and select the samples that you want to collect. Timing is everything. There's huge seasonal variation, and realistically one of those, the variation between ice and water is a profound chemical change. Phase transition, and so sampling at the right time to understand where it is within that ice-water continuum is really important. So here you can see on the left-hand side, we got there just at freeze up. The surface waters are still running. There's a little bit of water flowing down, but mostly it's just on the freeze up. The problem, of course, with sampling at that time is it gives you the nexus between the two, but is that, of course, for groundwaters, if you want to extract them, you've got two problems. Firstly, any kind of freezing will extract ice from your solute, and you will not have an accurate sample because of that extraction. Also because it clogs the lines because they freeze, and so over last summer I and James designed and built this new sampling device, which is able to extract the water subsurface, and then you bring it back into the truck and extract the water from there out of that reservoir at the bottom of that sampling device. It's pretty nifty, works extremely well. The other issue is, where is the permafrost? What is it's a movable boundary, so where do you what's the correct bore? Well, the simple thing is you produce more than one bore at different horizons, so you're getting some kind of profile of water chemical changes. So this is the research site. It's sitting about 9 kilometers out from Inuvik. It's a gravel pit that, as you can see, is still pretty fresh and new. If you look at the inflow arrow there, just below that you'll see IDP 07 with a 196. That's the ground and surface water chemistry of that pit, of that site, in terms of sulfate. So the numbers you see here are all sulfate. The yellows are surface waters where they still existed and hadn't frozen, and the white is ground waters where the surface water had frozen and you could just get below. So what you see there is clearly that in the pit itself there's a very, very large increase in sulfate associated with the pit waters in comparison to the inflow waters, and that continues all the way down to the outflow around IDP 04 on the left. What is interesting about this is that essentially the surface waters are the same sulfate concentration as the groundwater. This is essentially groundwater that's come to the surface. The large increase along with permacast and various other pit ponds, etc., indicates that there's active melting and active re-equilibration going on in this pit. And if we see that in the chemistry, now the chemistry of this pit was monitored as part of the ITH development, and if you actually look on the mining duration on the left-hand side of that screen there, the pit was active from 2014 to 2016. Unfortunately, we don't have data pre-mining, but what you see is there are very large changes in solute concentrations, conductivity, sulfate, uranium depicted here, but there's a whole bunch I could show you. And essentially the low concentrations are the initial spring melt, and which produces much more dilute concentration, but the vast majority of the data points are up with the groundwater. So these are sort of surface groundwater interactions and your seasonal cyclicity in chemistry. One of the interesting things is, of course, here's the CCME aquatic guideline for sulfate. We're way above that. Similarly for uranium, there's the uranium guideline. Good chunks in the green here are well above that, except for where you get low concentrations associated with surface unimpacted runoff at IDPA 07 there. And since mining has ceased, concentrations haven't changed. In fact, if anything, they've gone up a bit. Next, of course, we were going to go out in April, and we were going to take the companion data to that and look at the ice, so that we actually had water chemistry and ice chemistry, so we could actually play off on the two components of the system. Unfortunately, COVID travel restrictions meant that didn't work, so we've got to go to theory. Making a few assumptions, you can generate a model that shows how brine is concentrated as water freezes out from it. And as you see by the sulfate concentration line here, it just goes up and up and up. And in the last 10% of water's fraction, and remember this is permafrost, so everything freezes, you get incredibly high brine concentrations. But here, gypsum isn't the only one. There's aluminium sulfates that are saturated as well. But so obviously there's quite a lot of potential for precipitation in this system. What I really want to point out is the high salinity in bicarbonate, which is in the orange here. The bicarbonate, that spells trouble for clays, and this is what we're seeing in this area. Clays will dissolve in those kind of situations with the kind of pHs that we've got. So we have a pretty good idea of what might be going on, but we just can't prove it because we couldn't get out there and get the... So in tentative conclusion, almost guaranteed that permafrost melting is a likely source of the high solute loads. The obvious question is, how did the permafrost obtain those loads? There's nothing in these rocks that suggests that these kind of concentrations should be sitting in the permafrost. What's generating that? Well, I think some of these potential dissolutions might be doing things like that. Groundwater dominates the seasonal water chemistry in this pit. Seasonal phase transitions, as you can see, should generate highly saline CO2-rich brines. The role of those brines and the water rock interactions that they instigate are poorly understood, but I think we need a lot more work to figure that out. But on the bright side, the sampling techniques to solve these problems are now developed. We can take the samples we need. Thank you, and there's my contact details if anybody needs them.